Our next speaker is Michael Pilquist. Michael, as you all know, is one of the major forces behind Scodec, and we all know how awesome Scodec is. He is also one of the contributors to CATS. He is currently a chief software architect at Comcast. So a round of applause for Michael.
Thanks for that introduction. So today I'd like to talk about Scodec and how it uses Shapeless. And I have to say this is the first conference I've been to where there has been more talks with dependent types and generic programming and the things I'm going to talk about than not in a given agenda, which I think is great. I'm really glad to see these techniques getting adopted. So anyway, what I'd like to talk about today is I'm going to do a brief introduction to Scodec. I'm going to look at shapeless encodings of both HLists and coproducts and how those are used in Scodec for working with binary. And then at the end, depending on time, we'll get into shapeless encodings of records and unions and also how we apply those to binary encoding and decoding. Just a quick note about me. I work at a company called CCAT LLC. No one's ever heard of us. We do have a website now, thankfully. We've been around for 10 years, so that was a good milestone for us. But we are a joint venture between two large companies, between Comcast and Aris Group. We build control systems, and our control systems typically manage like cable set-top boxes, other clients that are involved in like video delivery, some head-end devices and server devices that are involved in head-end video delivery. And as such, binary becomes a very important part of our business. We use binary for tons of different protocols, and that sort of motivated the creation of Scodec. So Scodec itself, it's a set of Scala libraries. Today we're going to be talking mostly about Scodec core and its dependencies on shapeless. And I do want to point out that Scodec core is the only dependency it has is on shapeless. But it also depends on an internal library called Scodec bits. Scodec bits is your answer if you're looking for a replacement for a byte array, but you still want performance out of it, yet you want immutability. So Scodec bits provides like two primary data types, bit vector and byte vector. I'm not going to talk about them a lot today, but it's zero dependency. Once it reached 1.0 state, it has never had a binary incompatible release. That is going to change soon, but I'm going to go with that for as long as I can. And it is really intended to be like a foundational library that is safe for other library developers to use without avoiding or without running into class path trickery for downstream applications. There is a project called Scodec Stream that builds on Scala Z-Stream, soon to be FS2. I'm not going to look at that all today, but if you need to work with like infinite structures or very large binary structures, things that you don't want to do on heap, we do have an answer for that. There's also interop with a lot of different libraries in the ecosystem, so CATS interop, Scala Z interop, and so forth. The core algebra of the library is just this. There's two main types, encoder and decoder. An encoder of type A just encodes a value to an attempted bit vector. And so this is like the first method I've shown, and already this is sort of out of the norm in a sense. A lot of serialization libraries represent encoding as a total function. Here in Scodec, we want to allow an encoder to fail to encode. Earlier today, Paul talked about this notion that if we restrict ourselves to totally defined functions, we either have to restrict the type input in some way. An encoder of type A, imagine A being an integer, for example, would have to be able to encode all integers. But at any given point, we had an encoder that maybe can only fit like 0 to 8191 into the binary representation. We needed some way out of that. And today we saw two different options. We saw one option that sort of new typed or boxed the type A into some restricted domain. We also saw an option where we widened the output type. We said rather than returning a bit vector, we could widen it to some error carrying type. Here we have a temp. It's an Scodec specific data type, very similar to either our Scalactics or CATS' XOR, except the left-hand side, if you will, or the unsuccessful side, is an Scodec specific error type that carries additional error information. We'll see some examples of that. So we have a decoder. A decoder is, in a sense, simpler. It's just given a set of bits as input, attempts to decode that to a value of that type A, as well as return a remainder, any bits that were left over that weren't consumed. So if you will, imagine a 32-bit integer decoder it can consume 32 bits from that input bit vector, yielding a successful result with the input less 32 bits as the remainder. And then one way to think of a codec is that it just mixes in encoder and decoder, but that's a bit of a superficial way to look at a codec. The way I like to look at it is that it's an effect that describes a binary representation. And we'll talk about that. I haven't quite said that a codec is a type class, because we're going to see like a codec of unit, for example, that can represent many different binary representations. Borrowing Bill's abundant type class, or type class abundancy, excuse me, we could look at codec as a type class in that sense, but if you value type class coherence, codecs certainly would not qualify. So let me just give some examples first, and I want to show some basic usage of the library before we get into how we use Shapeless. So here we have three very simple case classes: a point that's made up of 2 ints, a line that's made up of 2 points, and an arrangement, just a vector of lines, right? We instantiate that and assign it to a val ARR. And we just have a point from 0, 0, or a line from 0, 0 to 10, 10, and another line from 0, 10 to 10, 0. Right away, if we add these two imports, an import of scodec.codec and everything in the implicits package object, what we're able to do is encode that arrangement to some binary representation. And I say some binary representation because we didn't really have any influence over the way that these types were represented in binary. We can sort of see, like, we've got a 2 in there in the beginning, and we had 2 lines in our vector, so maybe that's related. To the far right, we've got some like 0A, hex characters. Maybe those are the point 10s in our arrangement. But we didn't really influence the format, the binary effect itself. And of course, we can reverse that. We can take that binary and decode it. Each of these cases, encoding and decoding, we call this require method, which is sort of like unwrapping an option. It's great. It's a slideware feature, right? It's great to put into a slide, so I don't have to explain all the details. Or great to use in a REPL, but we typically wouldn't use require in like production code, for instance. So what actually happened on that previous slide is that we did like compile time reflection, if you will, using Shapeless. We looked at the various fields in all of those case classes, and we produced some binary representation that was influenced by the implicit codecs that were in implicit scope. So as one way to manipulate that, to get some influence on this binary effect, we could change implicit scope. Here, with some fresh scope, we will import everything from the implicits package except for our implicit integer. And then instead, we'll define an unsigned 8-bit integer codec in implicit scope. This scodec.codecs.uint8 is a constructor that just gives us a codec back. And then if we try to encode our same arrangement, you can see we get the 72-bit bit vector. It's much smaller, right? So we've taken every integer throughout that structure and shrunk it to 80 or to 8 bits. But what happens if we do that same example with this other arrangement, where the right bottommost value is a -1? Previously, it would have worked fine. It would have been a successful result, and everything would have round-tripped no problem through the codec. But here, since we have an unsigned 8-bit integer codec in implicit scope, what we actually get is a failure. And it says -1 is less than the minimum value 0 for an 8-bit unsigned int. But what's interesting is you get a path to the field that failed to decode, or failed to encode, excuse me. So it says, like, starting at the root of the object that you tried to encode, go through the lines property into the first element of the vector, into the end property and the y property, and that's the field that had the problem. So again, like, getting these fields names out of it is enabled by Shapeless, and we'll see some of that today. So that's like the lowest bar, though, that a serialization framework could meet, is that, like, we can round trip things through encoding and decoding. And we can write reasonably concise code and end up with a representation of it. What Scodec is about is really working with explicit codecs instead. I say explicit codecs in the sense that, like, I want to care and feed my binary representation. I really care exactly about the way it shows up. I don't want a framework making decisions for me about how my types are being represented. So in my line of work, I tend to work a lot with protocols that are formally defined, sometimes that they're 20 plus years old, like ISO specifications related to MPEG video, for instance. And I really want a concise way to describe those formats, a type-safe way to describe those formats. And I want it to be completely referentially transparent and composable. So this is one of the first examples of the way we do explicit codecs. This PID data type is from the MPEG transport stream specification. And really, we're just like new typing an integer here that's bounded from 0 to 8191. It's a 13-bit unsigned integer. And we can define a codec for that. In fact, PIDs are so common throughout the specifications that we've decided to put it as an implicit val in our companion object of PID. And we can do that by first constructing a codec that handles unsigned 13-bit integers. Here we're using this uint constructor, passing 13 as the bit size. And now what we're given back is a codec of int. But in some way, I want to convert that to a codec of PID, and we have two options. The first option is we'll just provide two functions, like an isomorphism between those two types, and what we get back then is a codec of PID. A different option, though, is to use this as syntax. And this as syntax is probably one of the most magical features in Scodec. It shows up in lots of different places. It's completely driven by Shapeless. There's all sorts of different options. But for now, let's just say that as can rewrite this as PID method into the xmap call above. And we'll look at more detail of using as. OK, so this is more of a production type case class. Not quite, but the fields here aren't particularly important. This describes like the beginning of a MPEG transport stream that's carrying one or more video programs. The point here is that there's like 3 booleans, there's some specific data types that's part of this domain, this PID data type and a continuity counter data type, some other integer fields. And this is how this might look with Scodec. So it looks quite a bit different than just that simple call to xmap a moment ago. So on the right-hand side, what we have is like a column of codecs, a column of types that describe the field types of each individual field in this case class. On the left-hand side, we have labels. And these labels appear anytime there's an error encoding or decoding with the field on the right-hand side. And so then we have like this kind of list kanzi looking operator on the far right. So we're putting all these things together in some concatenated way and eventually converting them all to our case class. And so what I hope to show today is how this all works, how Shapeless powers this particular feature set. So none of those examples actually used any Shapeless syntax at all. I tried to show some of the imports. Some of the slides showed all of the imports. But nonetheless, there were no Shapeless imports anywhere. We didn't reach for any Shapeless HLists or any other features directly. But nonetheless, these examples so far have touched on at least all of these features in Shapeless and probably a few others that I forgot to mention. So the Scodec itself doesn't hide Shapeless usage at all. It does depend on Shapeless very much. But nonetheless, you don't have to know Shapeless as a prerequisite to work with the library. In fact, I know quite a few people that use Scodec and either aren't aware of a Shapeless dependency, short of it being on the class path, or prefer to work with like tuples, for example. So just to kind of get a feel, how many people have looked at Shapeless HLists before? OK, great. So we're going to breeze through this part. So Shapeless HLists, a way to represent a tuple n is a good way to think about it, where we can abstract over the arity. We can write a single method rather than writing a bunch of overloads or some code generator that generates all of our overloads. Write a single method that operates on an HList, but nonetheless has the same features that a tuple n has. So we know how many elements are in the list, and we know the type of each individual element. So one of the first things we can do when we try to bridge Scodec and Shapeless is to just put codecs into an HList. So here, this has all imports. Here what we're doing is constructing 4 individual codecs, 2 6-bit integer codecs, one codec that's of type codec unit, this ignore 4 thing, which has the binary effect of just advancing the bit vector, just advancing the remainder, but not actually returning a value, short of unit. And then we have this Boolean codec. And what we're going to do is put them all into an HList, and we end up with this codec of int, cons, codec unit, cons, codec Boolean, and so forth. And probably one of the most fundamental operations in the library is this transformation here, where we have an HList of codecs, and we want to convert them to a codec of an HList. So if you will, we're sort of sequencing this HList. Or inverting the order of the type constructors. We're taking like the hcon type constructor from Shapeless, and sticking codec into it, pulling hcons out. And so what we end up with here is a codec of the HList int cons, unit cons, boolean cons, int. There happens to be syntax for this from Scodec that's enriched onto Shapeless HLists. We just call it to-codec. But this becomes so fundamental, this operation, that there's special syntax for it. Just to be clear about what's happening here in the effect space, if we go to decode a given input bit vector, the bit vector is fed to the codec of int. Assuming that's successful, the remainder of that first codec is fed into the codec of unit and so forth. So it represents bitwise concatenation of the binary effects of those codecs. So this transformation is kind of interesting, that if we have an HList and every element of the HList is an applied type constructor of the same type constructor, in our case it was codec all throughout, we can sequence it. And we can sequence it under two conditions. One is if the type constructor has an applicative functor instance. And codec does not. Codec cannot have an applicative functor instance. But another condition is that if the type constructor has an invariant lax-monoidal functor instance, and it's a bit presumptuous for me to put this on the slide and not mention it, but this name I invented in a sort of loosely based way that extends the research on lax-monoidal functors with some notion of invariant functors and tries to merge these two concepts together. Nonetheless, codec does actually have an instance there, and as a result, we can perform this operation. So I said it has special syntax, though. And so I should take this moment to apologize to Miles for kind of co-opting his operator. But then again, he sort of co-opted the one from list. So notice these two examples, val CS and val C. The only difference is that the first one has a cons HNIL in the end, right? And due to the right associativity of the cons method, what ends up happening is this gets evaluated as we start with a codec of int, and then we cons a codec of boolean onto the front of it, and immediately we get back a codec that's been lifted into an HList. So we get back a codec of L for some shape, boolean cons int cons HNIL. And we can move forward and eventually build up this codec of int unit boolean int HNIL. So this ends up being probably the most commonly used syntax in the library, this notion of building a codec for a product through this cons operator. And there's a lot of different examples of this in the library when just working with codecs of HLists. There's a lot of different combinators that, given a regular value codec and a codec of an HList, or vice versa, or maybe a codec of two HLists, we can put them together in various ways. A lot of these are just codec-specific rewritings of primitive HList operations. So, for example, if you can concatenate two HLists, right? As a result, we concatenate two codecs of HLists, and we just get back a codec of a bigger HList. But here's an interesting one. There's this operation called flat prepend. It does have this operator alias, which I should probably also apologize for. It's sort of like a squid turned to the left, greater colon tilde, right? And we, I actually use this data type in some production code, this case class here. So what this case class describes is the binary header that's written at the front of PCAP files that are written by Wireshark or TCP dump. And that file format is optimized for the speed of write of the system doing the capturing, right? So it's optimized such that it's really fast to read, and it's okay to have some penalty it's really fast to write, and it's okay to have a penalty to read the file back. As such, all words in the file, all integers, let's say, in the file, will be written in the native byte ordering of the system doing the capturing. So when you open Wireshark or you try to process this with Scodec, you have to somehow detect the native byte ordering and then change the way you process integers based off that. And so here's how we do that with Scodec. The general idea here is that there's this magic number. It's a known 32-bit quantity. We read that value in, and when we read it in, we'll get back one of two values. If it's a big endian architecture, we'll get back one value, and if it's a little endian architecture, we'll get back another. And so this byte ordering codec here that's used on the first line is a type of codec byte ordering that just reads the 32 bits and then looks at the two values it got. And the net result there is that it's a codec of type byte ordering. So if you will, we can sort of flat map that kind of but somehow have like this runtime dependency on the decoded ordering. Take the decoded ordering that came back, look at it, and then decide how to use that throughout the rest of the file structure. In this case, we have this special constructor guint16, another one guint32. Each of those special constructors just take an implicit byte ordering and then use another combinator to select one of two integer codecs. Returning to as, though, we saw another example in that previous slide of how we used flat prepend, or that silly operator, to stick a byte ordering in front of some HList shape. And what we ended up with was this codec of this big byte ordering with 3 ints and 3 longs. And our case class had that same type alignment, right? It started with a field of type byte ordering, and then had 3 ints and 3 longs. And we were able to use this as method to do the transformation, to convert the codec of the HList into a codec of type pcap header. And we say we can do this for any codec of a HList L. We can convert that to a codec of a case class if L is the generic representation of the case class. Or maybe a better way to say it is like if L is close to the generic representation of the case class, given a couple additional features from Scodec. So for example, Scodec does support like single element bindings. So we saw that with PID. We said we had a codec of int, and we used as to get back a codec of PID. We didn't have to first lift a codec of int into a codec of a single element HList. So it's one special case. Another is that it handles like automatic unit removal. So remember, like we use units in codecs to represent effects in the binary, like skipping over certain bit patterns. And so like if we had this case class of point with 2 integers, and then we have some kind of strange codec that's got like these 2 effectful actions in the binary representation, we can still use the as operator to do that binding. It will work absolutely fine. And really all it's going to do is remove all those units and then use the shapeless bindings to do the conversion. The sort of the workhorse of as is shapeless's generic representation. How many people have worked with generic at this level? Okay, quite a bit actually. So shapeless's generic implementation, we can ask for any given type T, we can ask for some generic representation of it that's represented as an abstract type member on the trait. We'll have 2 operations, to and from, where we can convert from a value of type T to its generic representation, or vice versa. This is the only macro we've seen so far. This macro here in the companion object for generic, implemented as an implicit macro, is the first case anywhere of macros in Scodec that we've seen in all the examples. So Scodec itself, Scodec core, has absolutely 0 macros, and everything just builds off of Miles's work, which is pretty convenient for me. But nonetheless, what we're going to do is build an HList up for all the fields in that case class. Moving on to another concept from Shapeless, we have the notion of coproducts. And how many people have used Miles's representation of coproducts? Okay, so not quite as many as HList. Again, there were quite a few talks referencing coproducts today, although I don't think anyone's covered Shapeless as yet. So a coproduct's just going to represent like an either n, if you will. An either that I can have a choice of exactly one type amongst any number of types. One good way to think about it is a set of right-nested ethers, but with nice syntax for working with it. It has a collection like APIs. We can do things like map and flat map and filter. Maybe not quite in the way that we're used to from working with standard collections, but nonetheless, there are ways to map these things. I want to look at syntax for a moment, because we're going to look at syntax quite a bit. And so the way I'm going to use Shapeless's coproducts today starts here with this type num. I'm going to define a type alias that'll alias this operator, or this type that says this type is either an integer or a long or a float or a double. So I'm going to pronounce this type operator : + : as or. And I'm going to use a type alias because I don't want to have to type that long type all of the time. The other thing I'm going to do is build like a pseudo companion, if you will. Or a convenient constructor for my coproduct, but I'm just going to give it the same name as my type alias. So I can say val num equals coproduct of num, where coproduct is the shapeless coproduct companion there. And what I end up with, stored off in this val num, is the ability to construct an instance of my coproduct type for any of the individual types in the coproduct. I can apply like an integer to num, I can apply a long to num, and so forth. but I can't apply like a string to num, for instance. So it's completely statically type-safe construction of my coproducts. So I'm injecting each of those values into the coproduct type. Another thing I can do with coproducts is I can select out any given type member of the coproduct. I can basically say, let's look at this coproduct as just a float, in which case ignore anything else, and what I get back then is an option of the selected type. So if I look at a coproduct as just a float, I'll get this option float back, and in the case of using like res3, where it was constructed from a double, I get back the value none. If I did the same thing and selected a double out, I get back an option double, but with the value sum. And you know, the operations supported on coproduct are quite extensive. They're basically exactly the same as the operations on HLists, barring some missed operation. But nonetheless, I'm not going to look too much at coproduct specifics today. Instead, what I'm going to look at is how coproducts are useful in binary representations. So the first way we're going to use this is this notion of a binary union. And a binary union basically is a set of bits that can be interpreted in a set of different ways. And I do not have any notion of how to select amongst these different ways. So here I have a coproduct type defined as ISB, which is going to be an integer, a string, or a Boolean. We'll create a convenient constructor for it, also called ISB. And now I've kind of done something maybe even worse than co-opting the cons method from Shapeless. I've co-opted the type operator, or, from Shapeless, but I moved it to a regular method I can use on values, which doesn't exist with Shapeless. And basically what I'm saying is that I want to build a coproduct, or sorry, I want to build a codec for my coproduct. And I'm going to say that it's either going to be a 32-bit unsigned integer field, or my bit representation is going to be a string, which happens to be represented in UTF-8 encoded binary, prepended with a 32-bit size field. That represents the number of bytes following that size field. Or it's going to be a single-bit Boolean. So I have a choice here of 3 different binary representations. And what I get back from that first line is not a codec itself, but rather is something that has 3 different representations, and we need to tell Scodec something more about the binary so that it can decide in what conditions to use each of these 3 options. And so this choice combinator that we're using on the second line, what it's doing is saying just try each in turn. So if you're fed a set of binary, first try to decode that binary as an int32. If that succeeds, take the decoded value, inject it into our coproduct type, and return it. If it fails, then try to decode it as a UTF-8 32, and so forth. So this is kind of interesting because this is an example of a codec that's not round-trippable. So I said, I don't look at codecs as type classes. If you did look at codecs as type classes, you might say, okay, what are the laws of this type class? And the first law you might come up with is that, well, anything I encode, I should be able to decode and get the same value. And this one does not, in fact, support that. So this is quite common that codecs do not always round trip. Some codecs do, and it's a useful property of those, but not all codecs do. This notion of choice is kind of a strange one. I mean, it sort of represents like a C union, right? If you think of the way structs are laid out in memory when building unions in C. But in Scala, this doesn't tend to be particularly useful unless you're doing things like versioned protocols, where you want to say try to decode some message as version 3 of my protocol. If it succeeds, then return it. Otherwise, fall back to version 2 and then fall back to version 1. That's typically the use case for this choice combinator. What's more typical is that we want to provide Scodec with some type of information about the binary structure such that it can decide dynamically at runtime which of the individual codecs to decode with. So here we call these discriminated binary unions. The notion is that the bit pattern is still a union, right? We still have 3 different options in our bit pattern. But before we get to the part of the bit pattern where we've got non-determinism, we were going to write some type of tag or discriminator to the bit pattern that when we decode our binary, we can read back, and then based off of the value that was decoded, then dispatch to the appropriate codec type. So we do that here via this discriminated by index method. We have to provide this discriminated by index method 1 argument, and it's the codec that's used to write out the discriminator values for each of the component types of our coproduct. So here we're discriminating by index. So we actually compute, like if you say encode ISB of 1, we compute that that's an integer. An integer is the first index of our coproduct, value 0 that is. And hence we're going to write a 1 byte 0 value into the front of our bit pattern. Same thing with strings and booleans. We get a 0, 1 and a 0, 2 in the binary output. So this is one way to do it. We can discriminate by index. It does require a codec of int as its argument, that u and 8 we're passing as a codec of int. But nonetheless, it does seem a bit arbitrary. This works great if your discriminators happen to be 0, 1, and 2, and you can you have some control over your coproduct ordering such you can define 0, 1, and 2 to match whatever your discriminator tags are. But this typically is not very useful. Extending on that, though, we get to something that's maybe a little bit more useful in that we can discriminate by providing a binding of discriminator values to the various coproduct component types. So here what we're doing is saying we're providing two bits of information. We're saying discriminated by a fixed size bytes codec, a codec that's going to write out a UTF encoded string that's exactly 1 byte long. So we're telling it how to encode the discriminator tag itself. And then we're going to say using some discriminator values of I, S, and B. And this sized type here is a shapeless feature. It's a size collection. And so statically, at compile time, this will only compile if you pass exactly 3 values, 3 strings, I, S, and B. If you try to pass a sized of 2 elements, it would be a compile error saying it needs 3. If you pass a sized of 4 elements, it would be a compile error, right? And you can see, like in the binary outputs here, with the same 3 encodes, we get the same values, but the first byte differs. We get like 0x69, 73, and 62. We're just writing out, UTF-8 encoded I, S, and B. So I wanted to take a look at the way this kind of pseudo DSL breaks down. I will point out, like when we started as Codec, we set out to build a DSL for building up these binary representations. And because we committed to a library that's focused on composition, we kind of dropped this notion of building a DSL. It's just the way codecs kind of plug together. Since everything is completely referentially transparent in the library, there is no difficulty, in a sense, in building bigger codecs from smaller codecs. So anyway, the notion of a DSL sort of went away, and it's just normal function composition and codec composition. So if we break down the way the types look here and start evaluating this, what we see is that we start by saying if we OR a codec of string with a codec of Boolean, we get back this thing called a coproduct codec builder, and it takes 3 type parameters. The first type parameter is the coproduct type that we're building up. The second type parameter is an HList made up, the HList that's like type aligned with our coproduct type. Except every element is wrapped in the codec type constructor. And then the third type parameter happens to be equal to the first right now. We'll see some examples later where it's different. The third type parameter represents like when eventually this coproduct codec builder builds a codec, what's its result type going to be. So we can do like some deferred transformations, if you will, on the output types. So of course we can OR onto that this codec of int, and everything's extended. All 3 of our type parameters get extended. We can then do that discriminated by call. What we get back now is this value called need discriminators of type string. It's this like projected type through our coproduct codec builder. And then finally we pass using sized ISB, which binds, again by index, right? But binds each of these values by index to the corresponding codec. So we bind I, S, and B to each of those. So if we take this notion of coproduct codecs and then extend it to sealed class hierarchies, we get something pretty powerful. And so earlier we talked about the generic representation of a case class is an HList of the individual fields from the case class. Here we can say the generic representation of a sealed trait is a coproduct of all concrete leaf types. Okay. So a couple people have mentioned like the sum of product representations or scrap your boilerplate. This is what we're looking at here. So if we take this example again from like the MPEG video space, we have the sealed trait tuning, and we've got 3 different options on how to tune a piece of content. We can tune by something known as a source ID, which is represented as simply an integer. We could tune by a PID. We have to give a frequency and a modulation and a PID. Or we could tune by this thing called program number. Also needs a frequency modulation, but takes a program number. So when we say, like, what's the generic representation of this, we'd say a generic representation of tuning is one where the type member repr has been refined to the coproduct that's each of those types ORed together. So how can we use that in Scodec? The general idea is that we're going to write a codec for each of the leaf types first, and then we're going to use this coproduct syntax we saw to build one for the codec itself, or for the sealed trait itself. So just kind of getting some boilerplate out of the way, frequency modulation, PID, and program, just assume they've been given to us somehow. They're just low-level data types. Each of those are codecs. Now, in our three codecs for our leaf types, each of those is just a case class. Each of those becomes very simple to build manually according to some specification using this con syntax, using cons and as, right? So like the by source ID case looks very much like our PID case from earlier. The by PID case, the second one, is a little bit interesting in that it's got this codec of units stuck in the third position, this ignore 3. Our PID data type, remember, was like a 13-bit in, and our representation of by PID is going to pad that, left pad it with zeros, so we can use this ignore 3 combinator. But nonetheless, the three case classes are pretty straightforward to define codecs for. Defining a codec for the supertype, though, we can do using this OR syntax with discriminated by and using. So we can just say it's a codec of tuning is a by source ID, by PID, or by program, discriminated by a leading 1-byte field. And if that single byte field is a 0, we're going to bind, we're going to decode the binary as a source ID. If it's a 1, we'll decode it as a PID, and so forth. Notice we get to use the as syntax, right? Because at the end of this, we just have a codec, so we get the full as support. Because tuning has its generic representation being a coproduct, we're able to use as there. That's all builds off of that generic representation support from Shapeless. But otherwise, this looks very much like the previous example. Some interesting properties of this syntax. One is that it will only compile if we have exactly one codec for each subtype, each leaf subtype of our tuning trait. So here we have by source ID, by PID, and by program. If we extended that with another codec, or we dropped one of those out, the as method would fail. The size, compilation of size would fail unless we adjusted for that as well. But most importantly, the as binding would fail. But nonetheless, there's still a lot of syntax here. There's a lot of things happening. And so if we can take certain liberties with our generic representations, we can do away with some of the syntax. And so I want to extend our notion of HList and coproduct with this idea of labeling. So how many people have used records and unions from Shapeless? All right, so now we're getting into the advanced features of Shapeless, right? So I'm not going to show the types because they do get a bit complicated. Instead, I'm going to use this syntax where we're going to take each component of either an HList or a coproduct and label it with a subscript. So here we have like this HList in string boolean. We could look at it as a different typed HList that the first component type is an int labeled with foo, the second is a string labeled with bar, and a boolean labeled with baz, right? And so if we extend an HList with the notion of labeling each component type, we end up with a record. And if we extend a coproduct with the notion of labeling each component type, we end up with a discriminated union. So like I said, I'm not going to look at the full type expansion of how we would actually represent this. Nonetheless, there is zero runtime overhead of this, this expansion. Just like John's work this morning, it does build on, or it does use phantom types. The encoding is just a bit tricky to fit all on a single slide. So if we take records and discriminated unions, and now we can apply them or combine them with the notion of a generic representation, and instead ask for a labeled generic representation. For case classes, what I mean by that is that we could label each component field of the HList with the name of the field from the case class itself. And for coproducts, we're going to label each individual subtype with the name of the subtype, the class name of the subtype. Okay. And so how can we use this to improve a bit on this codec of our tuning trait? The first thing we can do is define each of our individual leaf subtypes implicitly. So I've taken the same 3 leaf subtypes. I've changed nothing about them besides adding the implicit keyword to each of those. If we do that, what we can then write instead is just say codec.coproduct of tuning. So we're going to ask Scodec to say, basically that we want to build a coproduct codec for this trait tuning. We know we haven't provided all of the details necessary to do so. We have to provide the data type that's used to discriminate values from each other. We also have to provide a discriminator value for each individual coproduct element. But notice we don't have to specify like the manual construction of our coproduct codec builder. So instead, what this thing returns us is a coproduct codec builder. Yeah, Daniel.
So with the fact that you have so using sized 0, 1, 2, etc. on this coproduct tuning, I would assume that coproduct returned to us for tuning is based on the order that the case classes, the subtypes are defined.
Yes.
Your codec is awfully fragile then, because like if you sort of rearrange things.
Yeah, I was going to get right to that, but.
Okay. If you're going to get right to that, then never mind.
So let's take a look at what we're getting back here. We get this coproduct codec builder. The coproduct parameter, that first parameter, ends up being a discriminated union. So all we've done in this case is added the labels of the subtypes to each field. The middle type parameter is not a record. It's still an HList. We have labels throughout, but the labels are like inside our codec type constructor. So this is just a plain old HList. And then we have this deferred transformation occurring that's saying, once we have all the information we need to know about building one of these coproduct codecs, transform this thing to a codec of tuning. That's that third, the variance in the third parameter. So to Daniel's point, I actually did this intentionally where I use a different ordering earlier than what the generic representation ends up being. So I do have a bug here, right? This compiles. We went through all these great lengths to have this perfect approach to static functional programming, statically typed functional programming. And I have a bug because I didn't handle this reordering of my coproduct cases. And so what's happening here is that 0 gets bound to, I believe, by PID, right? Because the by PID type ends up as the first element of that discriminated union. So we can address this. I mean, so maybe Miles would argue that it's not fragile because we can know what the order is that Shapeless generates.
Well, so the order is the textual order of the constructor names.
Oh yeah.
So it's invariant under semantically neutral edits of the program. So if you swap the definition order of 2 case classes, that leaves the meaning unchanged and it's unaffected. If you change the name of one of the case classes, yes, that could potentially affect the order. However, you have actually made a semantic change to the program, so that seems fair enough.
You lexicographically order at compile time?
Yes.
Oh, of course you do.
Yeah.
Actually, my idea. Of course it was. Why did I even ask?
And actually, I set that up that way intentionally because I always think it's definition order. And at one point, I actually went to Miles and I said, I don't understand. Like sometimes it seems to be definition order, and other times it's not. And it was purely the lexicographical ordering that was confusing me.
You never cease to amaze me, Miles. You really never cease to amaze me.
So if you want to remain immune to such refactorings, there is an option. The notion is we can use records. So instead of passing a size collection to using, we can pass a record where we bind the name of each subtype as our keys, and the values are the discriminator values. So this has all the same properties as before. We have to cover every single entry in our coproduct. If we're missing one, it won't compile. We have an extra one, it won't compile. But there is a little bit more syntax here. We've got to import something to get this tupling operator or this record creation operator, the dash greater greater. That's a specific import from Shapeless. We certainly have to import Shapeless's cons and HNIL operators. And we do have this symbol thing to deal with as well. So there is more syntax involved. For my last topic, and then I promise I'll cede the floor to Miles, we can change this a little bit. And the notion is if we want to play games with implicit scope, if we're comfortable doing that, this is completely optional for the record, but if we're comfortable playing games with implicit scope, we can actually ask the compiler to do all this work for us. And the notion is that we're going to define an implicit val of type discriminated. And what we're going to say is that like the canonical way to discriminate subtypes of tuning from one another in binary is via a type int, and in binary we'll represent that int as an unsigned 8-bit integer. So we're providing a codec here to the constructor of discriminated. So this implicit val d has type discriminated tuning int. Then we bind each individual subtype to an implicit val, basically. But we're saying that the by source ID subtype is bound to value 0, discriminator value 0, and put that implicit scope as a value. And do that with each of the additional subtypes. If you do that, you can write codec.coproductoftuning.auto.
So I would argue that even if you're comfortable playing games with implicit scope, and I mean realistically, who isn't? This is sort of, I would consider this sort of an anti-pattern anyway, because you're putting your codec like sort of scattered across various definitions as opposed to all in one place.
Yeah. So there are ways to manage that. So it's common, at least for some of these data types, when representing formal protocols, where the case classes themselves, the sealed traits themselves, are defined in like a package that's specific to the protocol. So that's the first point, right? That it's okay to have like the codecs in the companions. The next is that, at least with this pattern, I tend to see this used where all of the subtypes of the trait are defined in the companion of the supertype. So then you really just have a set of these implicits all stacked in that companion. They end up being defined locally as a result. But yes, this is completely a trade-off as to whether you want to deal with this or not, deal with implicit scope. So the syntax for this, you can say coproductoftuning.auto, but you could also just say codec of tuning. And we've reached a point where we've actually completely derived a codec for a sealed trait in a completely automatic way, right? I mean, we did have to provide some implicit vals, quite a bit, but nonetheless, we were able to handle this derivation case. As a result, this codec of tuning, the last example there, where we just used the apply method on the codec companion, that ends up being completely compatible with like Shapeless's cached implicit feature set. So another way of writing this would be say implicit val of tuning of type codec tuning equals cached implicit, and now that would be computed one time. Cached off, cached as far as compile time is concerned, and you end up with a nice balance of features. So that's all I had for today. Just kind of some parting thoughts. One is that this is not all of our usage of Shapeless. Shapeless is used pervasively throughout the library, typically in ways that don't affect end users, but nonetheless, Shapeless is instrumental to Scodec's success. Scodec itself is very useful for working with binary. I've had lots of good feedback. Landon Fuller ported, or he was the original port of, or did the original OpenJDK port or pre-OpenJDK port to Mac, right? He ported Scodec to C++11. And it even includes a port of Shapeless's HList. So
sounds like Landon.
Yeah, it does sound like Landon. And anyway, I hope that what you take away from today is that Shapeless itself is absolutely pragmatic and is useful in real-world libraries. It's not just fun ways to extend what's possible in the language. So that's all I have. Any other questions? So I'm a bit over. I'll take one question. Yeah.
This looks fantastic. So it's just a phenomenal API. I really like it. Do you have any indication in terms of runtime performance compared to what you could achieve if you just did it manually? Yeah.
So it's funny because we started off by saying we laid out some design goals for Scodec, and our initial design goals were referential transparency, complete compositional API, things like that. I think they're still stated on the GitHub project if you look. And one of our non-design goals, or design non-goals, was performance. Some of the initial versions of the library, the data structure representing binary was actually a vector of byte, which you can't do much worse performance-wise, right? considering like the amount of boxing occurring in that particular case. Nonetheless, there's been quite a bit of performance work put into the library. You could certainly beat its performance if you are willing to sacrifice referential transparency, but otherwise, it actually handles quite a surprising decoding load. For example, we handle something like 20 megabits per second on just laptops, no problem.
I was going to say, just sort of like adding my random experience to it as well. Like we're using Scodec very heavily in some latency sensitive stuff, and we had previously had a hand sort of coded thing sitting on top of direct byte buffers of all things. And Scodec does support sitting on top of direct byte buffers with referential transparency, and the performance of Scodec is just like blew away what we had hand coded previously, like literally an order of magnitude better.
Wow.
And we hadn't like perfectly tuned what we were doing, but it also wasn't like the most naive thing ever. It was actually fairly efficient, and Scodec really is faster than what we did by hand. So I think we could beat Scodec, as Mike said, with doing things really close to scale. But I wouldn't want to, and I don't think I could beat it by that much.
Yeah, and the data structures alone as codec bits, if you do need like a replacement for a byte array or a set of bits, there's quite a bit of performance work that goes into making those referentially transparent but fast. So they're optimized for concat, right? Because we do lots of concatenation of very small bit vectors. There's some like mutable scratch buffers with races to like who gets to write the buffer, and whoever loses the race and then has to copy the buffer. A lot of techniques that were picked up from like recent refactorings to AutoParsec and some other libraries. So there's definitely some attention to performance. All right, thanks everybody.